Thanks, Yuri, for the introduction. Here are my slides. I hope you all see them. And during this talk, basically, I would like to first introduce, in a nutshell, what the Koopmans compliance is, and then just show how it performs in a sense, and draw a possible connection with a functional theory aimed at spectral properties. So how to extract spectral properties, or why we can extract spectral properties from a Koopmans compliance. So here is the actual outline, and let me start with the introduction of the Koopmans construction. So as also we heard yesterday, all of this boils down, or is rooted in the fact that exact DFT within a statistical approach with fractional number of particles gives a total energy that is piecewise linear. So exact DFT also needs to reproduce this exact feature. And we immediately see that when we go to approximate energy function, instead we have an unphysical curvature of the total energy that is no longer piecewise linear. Nevertheless, energies, or if you want better, energy differences at integer occupations are typically good. And when thinking of molecules, this is exactly the statement that the delta CF, that is total energy differences between n and n-1 particle, is a good estimate for ionization potentials when we deal with localized orbitals. And then if we look deeper into this curve, first of all, we remind Janak's theorem, that is that the first derivative of the total energy with respect to occupation is equal basically to the Kohn-Sham eigenvalue, because these are Kohn-Sham occupations. It is given to the is equal to the Kohn-Sham eigenvalues. So, like of piecewise linearity, somehow means that the derivative of the total energy is not constant with respect to the occupation. That is that an eigenvalue is not constant with respect to its own occupation. That was already mentioned in the past days as a way to define or to hint at self-interaction. So there is this connection from of piecewise linearity to self-interaction that is not complete, so it's not one-to-one fully overlapping ideas, but somehow there's a connection among the two. So in our approach, we would like to linearize the total energy basically as a function of all occupations Fi. This is not strictly required, but is sufficient in a sense to restore piecewise linearity, as I'll show in a second. And also by the end of this talk, you'll see that this is also able to convey more physical quantity. So in doing this, we are making a choice and doing something that goes a bit beyond, if you want, even DFT itself. To keep the global, describing the global picture, all of this is really rooted in the DFT plus U work of Matteo Coccoccioni and Stefano De Gironcoli, and then following work. So we have seen this picture of the linearization already yesterday and the previous day, so this should really come up very clear. And the earliest papers, at least from our own group on this subject, were these from 2009 and 2010, where this construction was first introduced. So in a nutshell, what we do is really that if we take our approximate DFT functional and we can write the total energy differences from n to n-1 or n-1 to n particles in this form as an integral of, as an integral over the occupation of an eigenvalue, basically we would like to substitute this integral, that is the one carrying the curvature with respect to occupation, with a term that has this form, that is an occupation times a constant that is reference eigenvalue to be determined, and then simply the correction that we have to add to the approximate density functional is just this term here. So this is the functional form of a Koopmans correction. How to determine this reference epsilon? Well, we here build again on the fact that total energy differences, when that is going to become clear later, but when orbitals are localized, are typically better approximations to ionization energies rather than the local derivatives like other eigenvalues. So here we can have several options. We need to estimate this slope, and that can be done by means of a Slater 1/2 approximation. That is, we take the derivative in the middle point, or in the Ki functions by means really of taking the integral, that is taking the slope out of the finite difference. Edward, sorry, Edward is going to give a detailed description of this that we call different flavors of the Koopmans function. This is nevertheless the key concept here, that is there is not just one Koopmans function, but in this construction you can have multiple according to multiple flavors. Here just a way to write some of them. I leave this for later. And then there is a third bit that is quite crucial, that is, so far we have been working formally by considering orbitals frozen, while in reality they are not. And so screening coefficients has to be added for each orbital, basically in front of the correction. And this is, if we compare with the DFT plus U construction that we heard of yesterday, is pretty related to the U itself. So it's a factor, if you want, in the U, and can be computed in a very similar way. So one could either use supercells and finite differences, changing the number of electrons, and compute alpha such that the HOMO of the neutral system is equal to the LUMO of the cation. Very similar also to some of the ideas discussed by Leo Kronig on the first day. Or, and this is Nicola Colonna's work, these alphas can really estimate by linear response, again, as U is can also be estimated using the HP code. Okay, so this is the construction in a bird's eye view, and it works. So somehow, if we look at the methane molecule, here is the HOMO eigenvalue. So we look at a function that needs to be piecewise constant, and black is LDA. You see that it is instead pretty much linear overall. Look, the scale is quite huge here. Instead, when we include Koopmans corrections, we start to build these steps, and KU is basically the unscreened or frozen orbital approximation that tends to overcorrect a bit, and instead K is Koopmans also including screening, and you see that basically we build some nice steps. Here is a clearer picture, just focusing at the total energy differences. And here come a slide about technical details. So what is the price to introduce this construction, at least in this formulation, is that we need to have functionals that refer to or are built on each orbital So they are orbital density dependent. They are not density dependent. So they do not depend explicitly on the density alone, but they depend explicitly on the on each orbital density. And this basically introduces, when going to the Euler equation to minimize the functional, this introduces potentials that are orbital dependent. And at variance, instead with the regular Kohn-Sham, regular DFT actually, where one has just, so if one takes this derivative with respect to the density, it's just one potential because there is one density. So all in all, this means that if we minimize the total energy by means of this equation, we end up having a set of minimizing orbitals that tend to localize. So because of this orbital dependence here, unitary invariance, as in DFT or Kohn-Sham, is actually broken. And so you have that different unitary rotations among the orbitals actually give different total energies. And experiences that typically the total energy is minimized with localized orbitals. So our minimizing orbitals basically look like Wannier functions. They are not exactly Wannier functions, so they minimize a total energy, not a spread function, but somehow that is the picture. And then this matrix here becomes Hermitian by construction, and so you may want to diagonalize it. And the basically what we typically interpret as eigenvalues and eigenvectors of a regular Hamiltonian problem, then that we call canonical orbitals, are basically the eigenvectors of this matrix, and these really instead look like proper eigenvectors of our system. So this is the way eigenvalues are estimated. This construction we'll see later on from Nicola Colonna also can be skipped. Still is quite important, as I'll discuss in the following. Here I also wanted to mention that basically we are not alone. That is, there are several efforts, really community efforts, building from different directions that somehow tend to converge to very similar ideas. And so this construction really relate with the short-range hybrids functions of Scuseria. There's a quite strong connection with the range-separated hybrids by Kronig and co-workers, with the dielectric-dependent hybrids of Govoni Galli, with the many-body self-interaction freedom idea developed by the groups of Wei-Tao Yang and separately John Perdue. And here, there's a nice recent review by Lior Kronig and Stefan Kummel, really discussing how the concept of piecewise linearity, self-interaction, correction, and Coulomb asymptotic behavior of the potential really connect, partly overlap, partly not. And here are also a number of other works that instead are really very close, very much overlapping with our KI function. I think more details are going to come in the later talks. Just want to mention that there's a lot of works, a lot of sub-pieces of the community really working on similar ideas. Now, let's look at how this works in molecules and solids. So here is the famous GW100 set that contains 100 relatively small molecules and deals with both ionization potentials and electron affinity. I think these results here are for ionization potentials, and this comes from a work led by Nicola Colonna in the group of Nicola Marzari. And you see here that there are a number of high level methods, GW, self-consistent GW, dielectric-dependent hybrids, quasi-particle GW, and so on. And KIPZ, that is one of the flavors we are using, actually sits pretty much among the best methods, really at a fraction of the cost, because some of these tend to become very expensive. So the first message is that this can really be very accurate in estimating ionization potential, and similar results were obtained by Giovanni Borghi for the G2 set. This applies also not just to the GW100 molecules, but also to larger molecules, especially these organic examples here related to large pi conjugated molecules, and this applies to both ionization potential and electron affinities. You see again that the average error bars for IP and EA are of the order of 0.2 EV. That is quite good, especially, I mean, if you take self-consistent GW as a reference, we are still doing slightly better, so that is very good actually. And not just frontier orbitals, so HOMO and LUMO, or if you want ionization potential electron affinities, but also deeper levels. Deeper levels in molecules and solids are assessed experimentally, accessed experimentally by means of photoemission spectroscopy. So here in black, we have the photoemission signal that we compare with the density of states still. So we are not including any matrix element, just the position of the peaks. But you see that the Koopmans corrected does a quite good job. It's important to notice that, okay, HOMO and LUMO at the LDA level are quite off within the gap. And often in the literature, people perform a realignment of local and semi-local functions to the HOMO peak. Here, there is no realignment. So this is the actual HOMO that comes out of the calculation that is pretty spot on the experimental one. And then we also have some decent description also of the low-lying states. Okay, so this suggests that we can go even a bit farther. That is, we can even include some description of the photoemission process. So we can include some matrix element related to photoemission, and we use the simplest approximation. So we use a plane wave approximation for the final state that amounts at computing this matrix element here. That is just a Fourier transform of the wave function. So we evaluate the matrix element of the dipole, the momentum, and here is an example of how the spectral look like. The top line is the experimental photoemission spectrum. Here is PBE at the bottom. You see that this is pretty much off. This is the LUMO, if you want, so empty states. These are the HOMOs, and you see that KIPZ is really able to reproduce most of the features, and now also most of the shape of the photoemission spectra. Here is another example applied to DNA, RNA, nucleobases, also including some sampling of the structural conformations of the molecules. Some of these have a finite probability of being found in different configurations. So we take an average over the different configurations and computed the spectra. And so we were able really to reproduce nicely the experimental spectra. Actually, this work was done by Lim Nguyen and Nicola Macari's group. And last but not least, one could even check the dependency on the photon energy of the photoemission signal. This typically is connected to the different sensitivity of orbitals with respect to the incoming photon. And so here you see that changing the photon energy from 21 to 50 V, basically we have an enhancement of this peak with respect to these other peaks that is well reproduced also within our theory. So far so good with molecules. What about extended systems? Here also our findings resonate pretty much with a comment made by Leo Crony. Basically, in order to be able to study extended systems, it's really crucial that we build the Koopmans correction on top of orbitals that localize. This somehow comes from the fact that bottom line, the accuracy of Koopmans is really related to that of delta CF, and if you do delta CF with extended orbitals, that doesn't work. It's this yellow line here that so works nicely for finite size molecules, and then it goes basically to the Kohn-Sham or to the Kohn-Sham eigenvalue here. Instead, if we work on localized orbitals and then build the correction, we are able to embody a real correction into the function, even for solids. And this applies also, so can be exploited to study band gaps. Here is the typical picture that we see very often for GW, and KIPZ really does a very good job. And here we can compare it over this set with other methods, G0, W0, and notably also quasi-particles of consistent GW with some vertex corrections in W. And so KIPZ is really performs pretty much as well as the most accurate method we have to date here in the table, and that is true also for the ionization potential of surfaces, and then to the description of bandwidth. So in a sense, so far so good, it works very nicely, but now it's time basically to ask ourselves why. So here I'm going to discuss the theoretical framework where all these lives in, to understand which are the key ingredients. And let me just remind this fact. Here we are, first of all, dealing with orbital density dependent functionals. As I said, these lead to orbital density dependent potentials. Energy is no longer unitary invariant. And at the end of the day, we end up with a eigenvalue-like equation that looks like this, where this potential is actually local but orbital dependent. And then this somehow says that while this method can still be seen within density functional theory, they are not Kohn-Sham any longer. Actually, if you want to cast them in a Kohn-Sham form, Korthdorfer and co-workers were able to work out a sort of OEP or generalized OEP method to minimize these functionals within a proper Kohn-Sham framework. But then the question here is there any added value in solving the ODD problem in this orbital dependent framework? And let me also remark that asking this question, so what is the framework we are using to solve our electronic structure problem, is quite important one. So we have to expect different behaviors if you are solving a system within Kohn-Sham or within, for instance, generalized Kohn-Sham, to name two, as very nicely remarked by Lior Kronig a couple of days ago. So in order to answer this question, let me start to construct an analogy that is, we have local orbital dependent functions. So orbital dependency reminds us of many body method, Green's function methods, and it enters the theory basically. If we look at Green's functions, we have a potentials that is given by a self-energy, non-local and dynamical. Here is the Green's function, Dyson equation, and we can perform this inversion by diagonalizing at each frequency, and then we can basically select the poles of this equation. And if we make a quasi-particle approximation, so if we retain only the so-called quasi-particle poles, we basically build up an equation of this form that is we have an object that is orbital dependent. So each wave function basically sees or is driven by a different potential. This is somehow related to this frequency dependence. Yeah. Then in a later work, Matteo Gatti and co-workers also showed that if you are interested in the local and dynamical spectral function, is the many-body formulation of the local density of states, somehow you don't need the whole information present in the self-energy that would give you the exact Green's function and all the plethora of information that is cast into the Green's function. But if you're just interested in the spectral function, it would be enough just to work with the local dynamical potential. So this should be enough to exactly describe the local dynamical spectral density. Here, the reasoning is pretty similar to that of DFT. If you're just interested in the density, it's enough to minimize your problem using a local potential that is the Koneschan potential. They just extended that picture. And if, again, you are performing a quasi-particle approximation to the spectral potential, so you're retaining only the relevant orbitals and the relevant frequencies, okay, you get that your spectral density in this quasi-particle approximation can be determined by a set of discrete local potentials, so local potentials that are orbital dependent. Then if we put this together, you see where I'm adding to. So somehow we have local orbital dependent potentials in ODD. Green's function theory, or the dynamical theory, basically can be recast within a quasi-particle or discretization approximation into orbital dependent potentials, and local orbital dependent frequency dependent potentials are basically enough to describe the spectral density of a system. So if we make a quasi-particle approximation here, we really reach back here. So we can interpret this construction basically within this idea of local dynamical potential. What does this mean? This means that the orbital dependent potentials of these ODD formulations are basically flexible enough to describe also spectral quantities. This doesn't mean that our ODD constructions are forced by construction to do so. So the accuracy is not built in. What we have built in this ODD formulation is just the flexibility of the theoretical framework to accommodate for also spectral quantities. This is not true whatsoever the accuracy for the Koneschan framework. So if you work even with the exact Koneschan framework, the fundamental gap is going to be wrong because of the derivative discontinuity that is not included in the eigenvalues. Here, this is not the case because we have multiple potentials. Okay, so also a reminder of Koopmans' theorem. We have, so just because we talk a lot about Koopmans, we have we meet Koopmans' theorem in the Hartree-Fock method as within the frozen orbitals approximation, we have that eigenvalues are total energy differences. Actually, I think it is worth to remind that this is an exact property of the exact Green's function. In the Lehmann representation, the poles of the Green's function that are our eigenvalues, if you want, are total energy differences n minus 1 or n plus 1. So somehow the case of Hartree-Fock is a corollary. Hartree-Fock is an approximate self-energy, and so this theorem holds approximately. This is also another view on the Koopmanicity or Koopmans' theorem. So let me now play a bit with these ideas more in particular before closing. And here I'm taking one-dimensional models treated, interacting models treated with soft Coulomb potentials, and this is a double well model, and we are basically solving the R3-Fock method that is non-local, and then we use the Schemschluter equation to compute the corresponding Koneschan potential that in this formulation, okay, when fully linearized, is known as exact exchange, but whether it's fully linearized or not here doesn't change much. So here is what you obtain, that is, you obtain the very same density by construction, but the only peak that stays the same is the HOMO, and that has to do with the fact that the HOMO determines the decay of the density in vacuum, and so that since the density is the same, the HOMO stays the same, nothing else. Okay, so spectral quantities are not reproduced in Koneschan theory. That doesn't come as a surprise. Instead, we can solve the Gatti Schemschluter equation, and we obtain a series of potentials, frequency dependent, and by construction, this reproduces both the density or the spectral density and the position of the peaks. Interestingly, we can discretize or make the quasi-particle approximation to our dynamical potential and obtain these green peaks here that somehow are able to reproduce nicely the R3-Fock non-local potential by means of local but orbital dependent potentials. And if you want here, what is important is just the counting. We have basically, in this case, 4 potentials, and we are able to describe 4 peaks. In Koneschan, we have 1 potential, and somehow we are pinned to just describe 1 orbital, that is the HOMO. Also, incidentally, we note that orbital density dependent R3 self-interaction correction in this case represents or reproduces very well, almost decently accurately, the R3-Fock. So somehow when orbitals are localized and not overlapping, R3 self-interaction correction is really a good estimate of the non-local exchange. We can do the same trick with the dynamical self-energy. Here is a model, so GW with a model screening. So you see that the black also has satellites and so on. We can do the same trick as before, and we do the quasi-particle approximation, and now we understand what this quasi-particle approximation means. Basically, we just retain the description of the main peaks, basically dropping the description of the satellites, but everything works nicely. And here is the potential, and here are we can have a look, a deeper look, if you want, at the shape of these potentials, because then one could ask, yeah, but this ODD or this frequency dependent potential may be very difficult to approximate. And if we look at their shape, we see that in this case, as I mentioned earlier, R3 self-interaction correction already does a quite good job in describing these frequency dependent potentials out of the Schemschluter. So here we are really matching ODD with the quasi-particle approximations to the spectral potential. And when we take the action of the potential on an orbital, the agreement is even more striking. And also, I probably haven't, I skipped this slide by mistake. An important statement here is that while in Koneschan we have to build a derivative discontinuity that is an exact feature of the exact potential, so needs to be there in the approximations. In these frequency dependent approaches, this is not the case, really. And here you see that a dissociation of a dimer, derivative discontinuity shows up, it's known in the literature, as an offset of the two wells that basically builds while dissociating. Somehow the situation is that we go from one HOMO to, when we are at dissociation, to two different HOMO levels that need to be described exactly. So the only thing that the Koene-Sham potential can do is really to build an offset to try to fix everything. There's a theorem that guarantees this, and the offset actually comes out. With spectral potential, this is not really required. We have a potential for each orbital, and that's enough to fix it. Okay, so here is again this picture that I've also shown on the first day, this hierarchy of methods here, and I really would like to stress that if DFT stays here, we can read. It's not mandatory to do so, but we can read this orbital density dependence construction in particular as a first step along this hierarchy here, where we have this quasi-particle approximation to the spectral density. So somehow we can inherit some spectral information. And here are my conclusions. So we have introduced Koopmans as a way to restore piecewise linearity. Several flavors exist, and accuracy that we obtain out of Koopmans is really remarkable. And somehow Koopmans compliant functions break in the ODD formulation, break the unitary invariance, so we are beyond Koene-Sham, and orbital dependency can actually be exploited, interpreted as a feature, not as a problem, and to bring us more information. And with this, let me thank all the my collaborators, or the people that have helped at first to build. And actually, there are more that we heard from in the next talk. So it's really a community that is increasing. And let me thank you for the attention.
Thank you, Andrea, for this very nice talk. We have some questions on Slack for you.
Yes, please.
The first question is from Maria Stojkovic. Can you comment on the geometry optimization using KIPZ for the molecules that you showed? Yeah.
So I think I showed probably some here. Where is it? Here. So that's a very good question. So I haven't discussed much of the total energies here. Actually, we had relaxed the geometries. So since the method is variational, we can access the total energy, so we can perform relaxations. And the very good point is that the total energy is not spoiled, and that is not too easy if you want to cast into your method. So there are a number of methods where you modify the potential, you get decent spectra, but then the energy is really spoiled. This is not the case here. KIPZ actually induces some changes to the energy, and for what we saw, especially in the with the works of Lin Guyen and Giovanni Borghi, on molecules we have seen improvements, like in the planarity of these molecules, in angles of other bonds. So whenever we have paid attention to geometries, we have seen some improvements, but the main point is that total energies are not spoiled. They are slightly improved, but PBA already has very often a good.
Thank you. So next question is from Arun Kumar Maurya. Koopman functional improves the results, those of DFT with LDA and PBE. The question is, why is it so? And what is the difference here from DFT in broad aspect?
So why so is, so somehow I tried to convey the message in the end of my talk that one of the reasons is that we go beyond the Koene-Sham scheme. So there are properties within Koene-Sham that cannot be described, like the position of the LUMO or the fundamental gap. those, even with the exact Konescham, are not going to be right in the Konescham scheme, while Koopmans going beyond Konescham is flexible enough to describe those. Pretty much similarly to what generalized Konescham with no local exchange and correlation potential can do. And the second part of the question, sorry, how does it compare with DFT in general?
Yeah, in broad aspect.
Yeah, so if you want, the question is, how do we, so if we had the exact DFT functional, what would we get, and so on. So here we really tend to correct for the over-delocalization error, over-hybridization of local and semi-local DFT. So of course, if you have the exact DFT, you have the exact total energy. And Koopmans does these two things. It corrects for over-delocalization, and while doing so, since it works in a scheme that is more general than Konescham, it also grants you access to quantities that were not in Konescham, that are these spectral quantities.
Thank you. Next question is from Jaimo Lim. Could you elaborate why orbital dependence is interpreted as frequency dependence and not as some spatial non-locality? Yeah,
that is totally right. So you can actually interpret the orbital dependency in these two ways. Actually, when we build, so the two are somehow equivalent to some extent. So one could cast one into the other. And this is also well described in the work of Matteo Gatti, where you can describe the effect of a non-local R3 Fock by means of a local but dynamical potential. And we can interpret, if you want, so decide which perspective to take. Even in our work, very often when we build the Hamiltonian, we end up with building an Hamiltonian that is made on projectors. So it's effectively also can be seen as spatially non-local. The two pictures, if you want, differ when you do not retain this approximation of one electron, one orbital. Then the two start to different. So then you have to have a quasi-particle approximation. You need to drop satellites and so on.
Thank you. And the last question is, can you comment on the phonon spectra in solids with Koopmans?
Well, I would like to do. No, I don't know if there's any work on that. It would be very nice to see. I think that if all these the corrections to total energies is one of the aspects that probably was investigated less. So I'm not aware if there's any work on that. Other Koopman people, please comment if you are aware of.
Thanks. And maybe one more, the very last question from Guido Fratesi. What is the increase in the computational cost, for example, for these molecules?
So here I think the computation, it depends a lot on the actual implementation of your method. Here we were using a Carparinello, modified Carparinello minimization scheme. And so eventually you have to rebuild your potential for each orbital. I think the calculation was still cheaper than an hybrid, but more expensive than local and semi-local DFT, of course. So it was kind of in between. I think the work, so both Edward Linscott and then Nicola Colonna could further discuss this aspect. One of the extra steps that is required is the calculation of the screen coefficient, so as the U, if you want, in DFT plus U, that also may take some time. But I really refer to Nicola and Edward for a better estimate of the timing.
Thank you very much again, Andrea. Let's move on to the next speaker of this morning.